Okay, let me share again the screen. And we can proceed. Okay, so it's me back again. Now we will start the last session of today, which will where we will talk about basics of high performance computing. So we will cover, we'll do some examples of parallel computing and performance analysis. Okay, this is going to be a very informal session where we want to start to really do some hands-on and training, give you tips, etc. So please really feel free now to interact with me and interrupt me as much as possible, because that will be the best for this session. So yes, I have very few topics, very few slides, and I will try mostly to do some hands-on together where we see some examples. And the main focus now will be performance analysis, computing paradigms, and parallel programming. Okay. So before starting, a few other things. So the slides are going to be on GitHub. So, and also the examples I'm going to cover. Christos previously mentioned that he will upload also his Jupyter notebook. We will try to collect now all the slides. So this is a GitHub web page that I've set up, and at the moment there are only my 2 classes. Now I'm going to give you the link. Hopefully now later today all the others will appear. Then so there where you can find the slides. Then okay, now next slide I will talk a bit about what is GitHub. The examples I will give you are all in Python. Yeah, Python, it's a programming language that I really like. I started to use it a lot in the recent years, and it's okay. We will talk about it quite a lot in the next later on. Yes. No, I cannot copy from here. So you're asking the link. I'm going to get it here. Then yes, okay, we'll talk also a bit about Python. These will be the examples. While on Wednesday, the main focus will be C with Openmp. And like Stelio mentioned, in the intermediate training, we will have a dedicated day for Python for HPC. This is because Python, it's not purely an HPC programming language. Actually, it's not at all, but its usage and applications grown up so much in these recent years that there is a lot of effort, there is a lot of requirement from the community to be able to use it everywhere for the data analysis. So this is an important topic to how to use Python for HPC. And yeah, just a notice, the examples I will give you may not work on Windows, so I don't know how many of you use Windows. With Mac will work for sure because they're based on Unix. And okay, of course, Ubuntu is my favorite operating systems, but yes, that's not about this. And of course, please interrupt me at any moment for questions. And stay online, that later on we will have some concluding remarks in the last 10 minutes. So I will try to don't take too long. So I know we are all tired, so this session will be very informal, and let's just gain some tips from it. Okay, so this is not really about HPC, but it's something very important if now you are going to deal with codings and with distributing your software, working with group. And this is an important topic that some of you may know very well, but I want to dedicate 10 minutes on it. That is version control and what is offered by Git and GitHub. So most probably I don't know, many of you, I could do a poll, but I think many of you already heard about GitHub. Maybe some of you are they have a user account there, they distribute the project. But So GitHub is a way to distribute online, is a platform to distribute online open source software with the world, basically. And I will switch now to the web page of it. They just to introduce it formally, it is based on Git. Git is a version control system. So version control means that it's a software that will allow you to keep track of changes that happen in your project, and changes that happen in your project. So it's everything. It's online, so will allow you to work in a community. You can work in groups, in teams on the same application, and you can split your project in parallel in different sessions, and then merge everything together and have some review process together on it. And it's very important when you're developing special scientific software, or in general, when you're developing software, to have a version control of system in plan for your software, because you may do a change that will destroy your code, and you want to be able to restore at any previous version of it. So GitHub now, it's the online platform, and it's used, I don't know, it's the most common online platform in the world. I think I don't know how many millions of projects on it, but it's a huge source of software where you can get resources from. And it's mostly for free. And okay, you can have some for payment services, but you can do everything for free, especially for open source. And it offers important tools that we are going to see in a moment. So let's switch to what I'm to the repository that I mentioned before. So basically, okay, this is a typical web page of a repository in GitHub. You can see the files, you can see some content of the files, you can see how many who contributed to it, and how advanced the software is. So you can see how it has been developed with the commits, and what changed time by time. And here you will this is okay. Of course, this is not an advanced repository, but let's jump to something more advanced. And yeah, let's take no, why doesn't work? No, sorry. So for instance, you can have, it allows you to have issue tracking. So you're working with a code, and this code is broken, you can easily open an issue, and the developer of it will reply to you. You can develop your branch and then try to merge it to the current. So for instance, this is a branch that is going to be merged. You can see what files in the software has been changed, what line specifically. You can put comment on it and say, okay, maybe it was better to written another way. And this is the way that you should use technically to develop a software in a group. So it's very useful if you're doing your personal project, or you're working inside your group. This is the way to proceed in a coordinated manner on the code. So don't lose track on the developments. And when you get, now I'm opening a terminal, when you get on a software, let's say, when you download a repository, okay, let's do it cleanly, just to have it, to show you how this looks like. Maybe, okay, my font is too small. So I can do, for instance, something like a git clone, and I get the new repository. And this will download the software that, or the source code that available online. Okay, this is slightly heavy because the presentation. So now I got in this directory the software. I can do something like Git Status and check what is the status of the code. So here it's telling me that I'm the branch main and there are no changes. Now, for this, I can start to do a change. So I can edit the README and add a new line here. Now, if I do Git Status, will tell me, okay, that file has been modified. I can ask for the diff of it, and it will tell me this has been added. Then I can commit the changes with a meaningful message and push them online. So this is in practice, very in 1 minute example how version control works. Okay, so yes, this you find it online, and please consider then to upload to whenever you develop something to do it in such a manner. And then also if you have a code online, it's much easier to collaborate with you. So if one day you want to ask us some question about your code and you want to work with us on some project, this is the perfect way to do it. Then, okay, another sidetrack topic is Python. So this is going to be the programming language I'm going to use today. In general, why Python? Well, a good motivation for why using Python is this chart here. So this is the, okay, in this case is the percentage of questions about Python on Stack Overflow. And you can see that between all the common languages, Python in the recent years has seen a very fast growth. And yeah, there are several reasons why the community decided to adopt it as a programming language, and especially the scientific community. So I know many of you use R. R, it's I think it's a programming language, okay, somehow similar to Python. They have similar purposes. I don't have an opinion on R because I'm not a user of it, so I put my hand forwards on that. I believe using R or Python for who is using R, would be very similar. And major reason why I think all of you are deciding to use R or Python are the tools that they provide. So when you are working with a programming language like C or C++, you mostly have to develop your software from scratch, from the low level. So there are libraries available, but most of the time is, I don't know how many of you have experience of developing software for with such programming languages, but those are more low-level programming languages. While when you're developing something with Python or R, I think the main advantage is the huge amount of tools you can use, and especially the huge community behind it. So yeah, here I try to list most of the reason why I like Python. So okay, it's science and data oriented, it's easy to learn and use, it has a huge community, there are thousands of Python modules that you can easily download, install, and run. It is the first choice for big data machine learning. That is not because Python has burned as a language for machine learning, but the main reason why people use it for machine learning are the modules available, like TensorFlow, and all the others that have been developed in such a programming language, distributed in these programming languages. Then everybody that wants to do machine learning, it's the first choice for doing so. The very big strength of Python is the fact that it's user-friendly and allows you to develop very great APIs. There is a question if Fortran is a common programming language. Well, it's a legacy programming language that was used in the past, yes. But nowadays, I mean, Fortran is another of those programming languages that personally I don't know. So it's very old. But these are the programming languages that are used in HPC. So yeah, that's the reason why I list here these programming languages and non other programming languages like Java, JavaScript that would have better, would be more popular, but they don't have applications for HPC. So two important features of Python that that make it a big and that make it a good programming language is how easy it is to deploy a software. So you can easily deploy a software suite that could work on any architecture, if you have Windows, Linux, etc. And you can easily deploy it to the world on Mpi. So every time you have done on Python something like pip installs, whatever, this will fetch the code from this online library of projects, where you can see this is where you can, for free, by your own, distribute your projects online. You just need to give it a name, and people can just install it very easily with pip. So yeah, this is one of the reasons. A second reason is that somehow Python proceeds with a scientific approach. I don't know if you ever heard about PEPs, but these are the proposal for enhancing Python enhancement proposal. And basically, if you want one day to change, I cannot scroll. Sorry. Yeah, okay. If one day you want to propose a change to the Python programming language, you could open a PEP. And so it's like writing a paper. You propose here your why this kind of change should be adopted, and what are the benefits of it. And these might be accepted and then enter in a new release of this of Python. Of course, like I tried to mention before, Python, it's not by its own a programming language for high performance computing. So this is one of the focus we will, this is one of the focus of the talk today. It's by its own, it does not do high performance computing. It's not like Julia or other languages that are interpreted and have focus on high performance computing. The main focus of Python is to be user friendly. Then if you are going to use it on a system, on HPC systems, you need to be somehow a bit more careful. It's still very powerful, but you need to be more careful. And this, I'm going to talk about it. So let's start from performance. Of course, it's in the name itself. High performance computing has as main focus the performance, together with parallel programming, but you always need to have in mind how well your code performs. In this morning talks, I already mentioned what is the measurement unit for performance in our field, and is the flop. So is the number of floating point operation per second. To give it a correct definition, one flop is how many operations you do, how many numerical operation like plus, minus, or multiplication you do per second. So that's the flop that we consider. So those are the operations we consider. Other operations like division, square root, sine, etc., are still floating point operations, but you cannot count them as one flop, because at level of hardware as well, they're not operations that can be done in one clock, but usually are done by some iterative loop. So these should not be included in the flop counting, or better, should be counted as more flops. And in order to know to how many flop an operation corresponds to, that depends on architecture. Okay. But when they ask you what is the performance of your code, and you need to measure the performance of a kernel, basically what you have to do is to theoretically count the number of operations you are going to have. So suppose you have a multiplication, this counts as one flop. Not true, this is already, the one needs to be careful already there. And then so you count the theoretical number of operations you're going to have, you measure the time it takes to execute it, and then so you divide this number by the time, and these are the floating point operation per second you do. Multiplication, for instance, also here you need to be careful. It's one flop if your numbers are real, but at the moment they're complex, this is 6 flops, because what you need to do is to multiply together the real and imaginary part, the mixed terms, and sum them together. So that's one example of something you need to think about when you're counting the flops. Okay. Another unit measures that we have in high performance computing is the bandwidth. So in this way, we measure with the memory performance, the I/O. And this is the measure of bytes that are read or written per second. Okay. So now we will do very soon an analysis of performance in Python. And here we will have our first notebook. And so, like I said, Python is a very powerful programming language, but it does not have a perfect computational performance. This is because it's an interpret programming language. So usually you have, when you write code in Python, you have you write some source code that it will be interpreted by, will be read by a parser, will be checked for some syntax, and will be converted in bytecode. And then this pseudo bytecode that is not really machine code will be executed by an interpreter instruction by instruction for then producing the result. And the interpreter is based on some compiled libraries. On the other hand, when you write your code in C, so you write some tasks, some operating instructions in C, these will be pre-compiled. So the full code will be translated in machine language. And basically, you just go from, when you run it, you just go from compiled code, you just use the compiled library, and you go directly to your results. So you are cutting off all these sections, especially the interpreter, which is the killer in the performance in this case. So the built-in functions in Python and the HPC modules that we are going to see are all based on compiled libraries and optimized libraries, and they try to use spend as much time as possible here in compiled libraries and as less time as possible in the interpreter. Okay, so let's go to do the example now. Sorry. So I'm as well going to use a Jupyter notebook. And I hope the font size you have here is good. So let me try to put it full screen.
Simone, if you can't hear us, we lost you.
I'm sorry. I hope I'm back.
You're back. Okay.
Yeah, thank you. Sorry. Yeah, I pressed the wrong button. Okay. Anyway, so I will try to write some code. I've prepared some notebooks that are available in the GitHub repository, but I would like to write my codes now by hand. So if you have this to raise questions and to involve you in this process. So so please stop me every time you have questions, etc. So let's start from some very simple operations. So now we start talking about performance. Okay. So let's start from a very simple operation where we define, I know some of you might not be familiar with Python, just try to follow what I'm doing, and I will not use very advanced features. And if you have some question about the syntax, but that's not the topic of today's talk, just the performance. So let's try to write a function that adds to arrays. So one way to do it, for instance, is to define a new list and then to have a loop over the variable, over the field. So let's do like this. And then I say that in the new list, I append every time then you append the value x1 of the component I plus x2 of the component I. And then I return the array, the new list I. Okay, so this is a function that is going to add to array. So for instance, I run add for a list, let's say 1, 2, 3, and I pass another list 1, 2, 3, execute it, and the sum is 2, 4, 6. Perfect. Okay. Yeah, of course, yes, this assumes that both arrays have the same length, etc. I'm going to do very trivial example just to give you an idea. So let's name this add1 with the idea that as next we'll follow some more we'll follow other functions, and let's try to analyze the performance of this function. So basically, okay, for analyzing the performance of it, I copied here a cell from the notebook. I will use the function timeIt. Okay, so timeIt is a function provided by Python, and the idea is that it will call our function a certain number of times. So let's provide a function. Okay, in this case, okay, we'll explain you soon why I need to use a lambda function. So let's do again the add example that I did before. Okay, and I say how many times this function needs to be run. I run it multiple times to have some statistics, and this will provide me the time in second that calling 100 times this function is taken. Okay, I need to provide a lambda function without arguments because timeIt wants to call the function by its own when during the execution. So I cannot time a result. It needs to time the call of the function, so the computation. So the way to provide a function to time it is to write it in this way. Another approach that timeIt uses is to parse to evaluate directly some string code. So okay, this actually didn't work because now it's add1. This should have worked. Anyway, you can maybe because it's not important, but you can provide directly the code as a string. Why now? Sorry, something has broken. Let's restart the notebook because I'm not sure what is the error there. Someone has an idea of the error? Add one. Why does it say it's a string? Sorry, I should not do this kind of test online. Yeah, anyway, let's keep going. Sorry, I'm not sure what was the error there, but I could investigate it, but not now. Maybe there is a parenthesis. There was a parenthesis, I didn't see it. So yeah, so I'm going to use timeIt, and the idea is to analyze the performance of this function I wrote versus some samples where I change the size of an array. So I take, in this case, I use just Numpy to create a random array of a certain size, where now the size is defined by this list. So basically now I'm creating here a list where with an exponential growth in power of 2. Okay, so I create this list. I'm going to run the function several times, 1,000 times in this case, and I'm going to get to analyze its performance. So I'm going to see how the time in seconds is growing versus the size. Okay, so we can see that let's call it, this was a bit slow, but we can see that the timing is somehow increasing linearly with the size. This is what we expect. We double the size, the function takes almost double time. Okay, so this was the performance. It's very difficult at the moment to say how well this function performs if we don't write other examples. Though if we want to get the performance of these now we get the performance by dividing the times with the size. So, or sorry, we divide the size. So this is the size of each array that we said it's an exponential. It's growing exponentially. We divide the size by the time it took, and we can plot these by simply doing. We copy this line and we plot it, and so this is performance. And okay, we can see that, sorry, this is times again. It's very difficult to write and talk, one gets distracted. So this is not a beautiful plot of performance. We will see how this changes later, but this is how many operations we were able to do per second, okay? So let's try to improve this code a bit. Okay, so what we are doing somehow not wrong, but what operations are costing in this code. An operation that is costing, suppose it's the direct access to the data of these arrays. By the way, maybe I could involve you a bit if you want. Maybe later we'll ask you some questions. Who wants to offer some other solutions, maybe? Okay, is there anyone that wants to offer another solution how to write the add function? So, of course, this we say Numpy, that is going to be my answer, but that is going to the purpose of this is to show you the issues of Python. Let's take, okay, remove the appending. The appending we will let's remove the appending now. So another step that we can do is to remove the appending. So if we don't want, this is an issue because basically we have a list and exactly what Panayot is saying. Here we have a list, and this list, we don't define the size of it, and we are extending it time by time. Okay, so every time we are extending it. Something we can do in Python, for instance, is to instantiate this as 0, and so first instantiate it and create it with the length of x. And okay, Panayotis is giving already the last example. I think it's the best performance you can get with Python. So we instantiate the list, and then instead of appending, we store on the component I. So these will not extend the list, but will replace the value. So now we have this add 2 that we added here, and we run it less time because now it took too much. Let's run it times 10. So I divide the time I run it by seconds. So what you can see is that our add 2 actually in this range here, it's not faster at the moment. If we instantiate the list here, the list in this way, and then we are trying to change the value, it's actually slower than the time it's slower than add 1. So it has a worse performance. A way we could instead, so this is a way you can try to change your code and see the performance. You just analyze the time and you proceed. Another way we can try to improve it is by not accessing the data directly, but using the zip function. So the zip function will access the data for us. So we'll fetch them from the array, and we provide us directly the value. So here, instead of accessing then the component by component, we can do I1 plus I2. So let's name this add 3. I add it to my list. And okay, now this is also due to the number of operations. These are some fluctuation in the time. Let's increase the size of it. You can see that this is showing to be faster. Okay, an issue we see here already is the fact that I'm running only this function 10 times. And you see that every time we have different results. For instance, now we saw that add2 is different, performs better than add1, because we are in a region where it's not so much the work, we are talking about milliseconds per call, and this one it's looking at fluctuations of the of execution time. So let's try to run it a bit more. This will provide us a better statistics and should provide us results that show less fluctuation. So you can see that now this new function at 3 is performing better than the others, because we are avoiding the direct memory access, but we are fetching the data. Let's go with the solution of Panayotis, that is the one that I'm proposing as well as fastest solution. And instead of doing all of these, we do an inline operation. And we say that we use the zip function to access the data, and we directly create the array without having to instantiate and to write in memory. So this add4 performs sorry, I didn't add it here. This add4 performs like this, so performs better. So you can see that add4 now it's performing better, and one can see, wow, I almost doubled the performance of that I had at the beginning. This is a great speed up. Ronnie, I'm going to reply to you in a sec. Okay, we reply to you now. So the zip function is iterating for you the data. So it's zipping together two lists, and is basically, I can show an example. If I do a zip of two array like this, the zip function will be a generator that I can list, and basically it's providing me, it's iterating the list and providing me the data in couples. So if I have 3 lists, I would have 3 values that are basically the first 3 values, then gives me all the second 3 values, etc. So if like now we have, we need to access 2 arrays, the content of 2 arrays with the zip function, we can iterate over it. Okay, I hope this was clear. But if for any question, Google is always, on Google, you can find a lot of answers that will clarify your mind. It's not like matrix multiplication, but okay, yeah. Let's go to the last example, that is, of course, to use Numpy. And let's have this add5 that where basically, instead of doing all this work, etc., I just return x1 plus x2. Okay. And now let's see what happens. Are you ready? Again, sorry, I didn't add 5 here. Anyway, should not change so much. Yeah. What happened now? It's 0. It's flat there. Yeah, this is the point. This is how Python is slow. This is the performance you have in C here. And if I go to, so the wow of Ronnie, that's what if you didn't know, you should have in mind. To access the data directly in Python, Python is slow to do that. So if I go in logarithmic scale, if I go to a logarithmic scale, we are talking about order of magnitude difference. So we are, when one is taking 10 to the 3, now we are taking something around 10 to the 6. Yes, add5 is NumPy array. I'm just doing x plus 1, x1 plus x2. And since, sorry, I didn't specify that. Since x1 and x2 are generated by NumPy, the built-in function of Numpy is something written in C. And so this is basically calling the addition of array provided by Numpy. Okay, so in that file, I'm doing nothing in Python. I'm just saying to Python, please call me the addition operation of Numpy. Okay, and this is the performance. So this is the real deal. This is what you need to look at. It's while all of these are increasing since the beginning linearly because they are pure Python operations, here we don't see an increase in performance. Why? Because what you're measuring here at the moment, it's all overhead. Doing this operation on 1 or on 10 takes the same time, okay? Our CPUs are able to process a huge amount of data with a very high performance, and this is the kind of plots you should look at. So if now I check again the performance, you see here, okay, this is maybe the scale is not good. Let's put it also in logarithmic scale again, also here. So because of course in this case Numpy is winning over the others. You can see that while now we are talking about, so I'm dividing by 100, so we're talking about flops, and you can see that Python by its own is performing 2 to the 6 flops, floating point operation per second. I'm sorry if the plot is too small, but these are flops here, okay? So these are basically mega flops, while with Numpy we're reaching the performance of gigaflops. So we're 1,000 times faster, okay? And here, as I told you, you don't see a linear increase yet because what you're measuring mostly are overheads. So if now I do the same that I'm doing here, but only for add 5 in order to be faster. And let me take also this, sorry. So if I do the same only for add 5, and let's go much higher, much larger value. So let's go to the 20 number of data. You can see that now this came out very fast because now we are talking, we are dealing with Numpy, so this came out very fast. And to process order of 500,000 numbers, it's taking 1.6 milliseconds. Okay, so this is the kind of scaling we have with Numpy. So if I put it in a logarithmic scale, you can see again that here we are measuring overheads, and then we are the linear scaling getting in. So this it's a real scaling of your code. These are just overheads. So this is the region you want to measure. And if I want to analyze the performance now again, in this way, you can see that, okay, apart this jump at the end, you can see that it has a sustained performance of 1 gigaflop, okay? This is what you should quote as a performance of your kernel. So your kernel has a sustained performance of 1 gigaflops because here we're doing one operation, that is the addition. So we're not doing more operations. If I start adding operations, then the number of operations starts to get in, but this is your performance of your kernel, not this area, this one, when it flats out. Okay, so you are eating the best your CPU can do. So it cannot process more than this amount. Any question? Okay, so the takeaway message about this part is that in Python, never, ever, ever do for loop on the data. So it's fine to do for loops, etc., to write Python codes, but the Python code should be mostly used to build the engine of it, the brain of the code that manage functions. But at the moment you need to process data, never use Python, use modules, HPC modules like Numpy. So you're still using Python, but you're using modules that have as a backend a compiled library where this compile library is written in C or in other languages, and it's written machine code. And basically, you are just taking the row array and process them, and you're not going through the interpreter. So what we did previously, yeah, let's go out again. What we did here, what we did with Numpy, we went, so in this case, yes, Numpy is spending all this time, so all these time in seconds that are, okay, 1 millisecond in this case, with this size, all these millisecond is spent in a on a compiled kernel. So it's not Python, it's a function is being called, and it is spent in a compiled kernel. So just on the machine, the interpreter is not be involved in that second. I understand why. Yeah. While on the other end here, all this in this region, all the time spent here, it's all time spent on the interpreter. So the interpreter is basically every time reading the iteration, accessing data, doing the plus, but this is done all at the level of the interpreter. The question of Panayota, why we want to look at the flat region, because this is where you measure your sustained performance. So this is where you hit all the performance your CPU or device can give to you. In this region here, you don't need the sustained performance because you are looking at some overheads. So here there is an overhead due to calling the function, for instance, that I'm measuring. You see here that doing 1 or 100, or adding 1 or 100 numbers, okay, it takes nothing, take order of microseconds, but it takes the same time. This is because you're measuring an overhead required by calling the function, instantiating, moving the data to the CPU, etc., and starting to process it. So this doesn't tell you the computational performance of your kernel. It may tell you this is not the metric you want to look at. What you want to look at is the region here where the cost of the overhead has been overtaken by the cost of doing the actual operation. And in most of your code, hopefully, you are going to work in this region. You're going to work with big data. And so you're not going to do simple additions that takes nothing, but you are going to run the kernel. Okay. Yes, so this is the first takeaway message of the day. Never use for loops on data in Python. And there are many ways to do so. So you can use Numpy. There are other modules, Panda, SciPy, all the TensorFlow is also always using C compile function for everything, for all the networks you are analyzing. And there are ways to directly compile your code. So if you have some Python code that you want to compile, there are ways to do it. So you can look at this library like Python, Numba. They are very seamless way to compile your code. And if you look at their documentation, you can try them out. And basically the idea is, for instance, this Python, is simply to have a decorator of a function, and this will be compiled. So inside your you write a Python function, and you just say to Python to export this function. So you give an instruction to like you will see for Openmp. You will just give an instruction in your code that, look, this function don't execute in Python, please compile it, and then call the compiled version of it. So I didn't prepare that, but what we could do is to try to compile with some of these libraries, these functions here. In the same way, as Python, you have Numba that wants to provide a seamless way to provide Python code. They have limitation, you cannot compile everything, but numerical operations, you can easily compile them. Okay. Next. So now we talk about, we go on the topic of So here I showed you some examples of performance analysis, what you want to do when you analyze the performance of a code. Now we go on the topic of parallel programming. So what are the computing paradigms we use in high performance computing? In the talk this morning, yes, sorry, Panayotis, want to ask something? Please go ahead. I forgot.
I think somebody else wanted to ask something before me.
I think I replied to Panayota's question. Yes, sorry. But please go ahead, everybody that wants to ask something.
Yeah. So Numpy is an optimized library, but don't we optimize our code dependent on our architecture? So how can this be general?
Okay, yeah, that's a good question. So, okay, Numpy, it's like many other libraries that you may want to write in Python. I don't have the slides now on the end of this morning. I can get them. Yeah, maybe it's better if I open them as well. So, and I can show you also some examples now. Yeah, that's a very good question. This is what I want for these. Don't be afraid of asking questions. We will talk about everything you're interested in. So what Numpy is providing to you is providing a Python API that you can use. So it's providing all the infrastructure in Python for seamlessly constructing array. I think this one. For seamlessly constructing array, so it's providing this beautiful interface that you can have access to in Python. But then together with it is providing a lot of code written in C that are kernels that are the actual implementation of the operation you're going to do. So for everything you do, then you are going to offload the task to a compiled kernel. And basically this is software that is written in C that at the moment you install Numpy on your system gets compiled. So it's task of the compiler to optimize the code that Numpy provides you for the architecture you have. As far as it's a CPU, Numpy doesn't run on GPUs. There are other Python packages similar to Numpy that runs on GPUs, but Numpy itself doesn't run on GPUs. But from the CPU point of view, the compiler will optimize the code.
Okay, thanks.
Panayotis?
Yeah, so my question is related to Python and these other tools.
Yes.
So I only have experience with Python. So if I had to choose one of them, do you have something to suggest or not?
Yeah, okay, that's another very good question. And if I don't, again, the best answer is to try them out and to ask Google. So if yeah, there are a very nice, how do you say, blog response that you can look for that Python versus Numba versus other. So this is, for instance, one example where they take the same piece of code and they will run it on Numpy, Cython, Python, etc. And they will show you at the end of the day the performance they get, where one or the other win. It's of course depends on the very small things. This is what I was mentioning also this morning on these other tools that like OpenCL or OpenMP that they try to provide you to answer to the most of what the community asks for, but then are very subtle details where they change the performance of the code depending on the case. So it's just a matter. You need to look to the API mostly and which one makes.
Okay, it was just a question to see if you have any experience with this.
I tried them out. I have experience with them, but personally, okay, except Cython, it is something else. Python and Numba both provide you this way of seamlessly compiling code. Numba is, I think a main difference is that Numba is a just-in-time compiler, so it's going to compile the code as soon as you call it, while I think Python will compile it you can compile it earlier than running it. I need to check this detail again, but yes.
And there's also the option of doing pure C++ or C and interfacing that.
Of course, I think is going to. I mean, these tools I think are one of the focus of the intermediate training at Python for HPC, because we will take really this example. I mean, there are a lot of tools that we can talk about, and there I really want to go over some tools and analyze how to use them. Okay.
That's great. Thank you, Simone.
You're welcome. Other questions? Okay. So, yeah, time is flying, but I will try to go over all the material. If it's not, it's fine as well. So the computing paradigm we see in the systems are on one end, multi-threading. So we said our CPU has multiple cores where multiple threads can run on it, okay? And as many cores you have, as more threads you can run within one node. And the main characteristic of multi-threading is that the data are shared. So all the threads can access and change the data at any time. Okay, so they don't have dedicated part of the memory, but the data are shared in multi-threading. That's the key feature that you need to remember. The difference between multi-threading and multi-processing is that in multi-threading, the data are shared, full stop. So you have a common pool of data, you do operation on it, and you have multiple cores working on this data, okay? And so just to have an idea, let's take a machine like mine. And if I do here now in Linux, you can access, for instance, this file CPU info, where CPU info will tell you the characteristic of the CPU. And you can see that, for instance, here we have a set of processes. This list goes up to from 0 to 7. So I have 8 processes. And you can see that my CPU has 4 cores, and these are all the characteristics of the CPU. You can access all the detail of it, for instance. This is one case here. Now, if I access instead a system like Cyclone, now I will be in the login node, but it has the same structure. So if I do, okay, by the way, now just I will mention something, but okay, if I access a system like Cyclone, now it's a more advanced model of CPU, which have 20 cores, and they have two threads can run on each core each. And so basically what we have here are 40 processors, okay? So tomorrow you will go in detail of this, but when we talk about HPC, we're mostly talking about the remote access of the machine. So the way to access the machine is through the SSH protocol. And most of the time, so tomorrow you will start with this, you will deal with a terminal, and you will submit tasks. So I don't know how many of you are familiar with it. If you use Linux, for sure you're familiar with it, but if you use Windows, you may have never used a terminal. And this is the way that you interact with the system. So you access to a system, you have this a bit ugly picture, where though it's very useful, because what you want to use it for is just for computing. So you submit jobs, you get data, and process and process everything you want to do. Okay, so this was about the CPU. So we have the physical cores, and then we can have virtual threads running on it. And in this case, most of the cases we have 2 threads running each. So up to 8 threads running in parallel on a CPU. In my case, where I have 4. On the case of Cyclone, it's 40. Another computational paradigm is GPU accelerated computing. This again I mentioned quite a lot in this morning talk. In this case, we have a device or multiple of them that have a dedicated memory, and they have a dedicated microchip that in this case is named GPU and not CPU. So it has different characteristics than the CPU, like we saw in this morning. So when you are dealing with this kind of structure, yes, I think I already mentioned it, but it's never, it's always worth to repeat things. So what you need to do, you need to take care of is of two different memories. One is the host memory, the one that the CPU has, and one is the device memory that the GPU has. And you have physically say to transfer data from the host to the device memory or vice versa. So the data that are on the GPU, okay, there are interfaces to see them, but practically cannot be seen by the CPU unless you try to access them. Okay, so are not data that the CPU can actually operate unless it offloads them. And they are different architecture. They require dedicated compilation of the code, and what you run on the GPU, it doesn't run on the CPU because really the architecture is different. So you need to do different operations. And to have an idea again on if you're on a system, let me log into our other system, Cyclamen. And here, okay, to give you an idea, for instance, this is a system where I can, with Sympho, I have 8 GPU nodes, okay? Can I allocate one of these nodes? So this will be tomorrow will be in detail, but now I said Salloc and I went inside one of these nodes. I'm on a computational node. And basically, if I do NVIDIA SMI, I can see that on this node, I have 2 Tesla GPU that which utilization is 0%, so nothing is running because it's a dedicated node. So this is a dedicated node that nobody is using except me. Okay, and I can locate multiple of these, and I have devices on it. So usually when you're dealing with these machines, you need to know the characteristic of a single node, and then the characteristic of the full machine. So how many nodes it has, etc. So the one you have now in like Cyclone, the one we have in Cyprus are quite small, but if you go on a larger system, let's take, this is the, sorry. This is at the moment the largest system in Europe. And if I go here, I do Sympho, you can see that there are many, this is how it looks like. So you have hundreds of nodes, and these are the nodes available, etc. And you can then access them. And so it's a system where you have a, sorry, my screen is not shared. Sorry. Okay, sorry, you missed. So now let me do it again. Now I'm accessing another system. I don't know when it stopped. There is this button that is sensible here. And so, yeah, for instance, now, as I was saying, this is the booster cluster that is the largest in Europe. And for instance, now I ask the characteristic of the machine, you can see that it's much bigger system where there are different partitions. For instance, this one has 2,000 nodes. Then this is the case of the GPU nodes are around 700, etc. And usually when you deal with these systems, you have they're constantly busy, and you need to deal with a queuing process. So when you do, but this is the topic of tomorrow, just to give you an idea. If I now do queue, this is the queuing process, and you can see that, for instance, these are the jobs running, this one here, and there are others waiting in the queue, etc. Okay, so they're waiting for their time to get in. So for instance, this one is asking for 4 nodes. This is run on 20, etc. Yeah, so like I mentioned this morning, you have very powerful nodes, but when you do HPC, you don't use one node, but you use a cluster. So you want to be able to access, to use multiple nodes, and basically the system just gives you a bunch of nodes that you need to start using. Okay, and this is the case of distributed data. yes, distributed computing, where the important thing is the data are distributed mandatorily. So each node cannot see what another node has. So it's not like multi-threading where the data are shared, or multi-processing, which are still within the same node and it's easy to access them. In this case, the data are completely somewhere else, and you need to ask to another node, hi, give me this data, I need them to do something. Hello, these are your data. Okay, you need to have this kind of communication, and this comes with a communication protocol. Any question on this computing paradigms? What is better, multi-threading or distributed? Well, there are two different things. If we were able to construct very, very fat nodes that are all where so many CPUs are inside one single node, of course, the answer is that is better multi-threading, but this kind of setup has limits. So this is the maximum you can put inside one node. Then you have limitation, hardware limitations. So the fact you come out with distributed computing is because you cannot put more hardware in one node, but you need to have multiple hardwares. And then that's the only way to continue with it. Okay, so of course, if you are within one node, the best you can do is multi-threading. But at the moment you need the power of multiple nodes, you must deal with distributed computing. Other questions? Okay. Now let's have an end-on on the multi-threading, and then I will have an end-on Mpi. So this is just to give you a bit an idea of what you're going to work with. So how do you do multi-threading? One way to do it is with Openmp. This is a very, very common way that is used in C++, because like I showed you in the example, that is where you want to develop your HPC code. So at the moment you are doing low-level code and you are dealing with operations, you are dealing with compiled code written in C++. So this is a tool available for C++ and Fortran Openmp. And the basic idea is that, like before, we had a for loop with a simple line. So you say Openmp parallel for. This for loop is not going to run serially. So I is going to go from 0 to 100, but it will be run in bunches, executed in bunches of a size by different threads. Okay. This, of course, requires that the operation, an iteration does not depend on the previous, but can be, this is just, for instance, a memory access like I was doing before with addition. So there are these conditions that an operation should not depend on the previous. There are low-level implementation available like POSIX threads, standard threads, or threading, but these are not the suggested way to do multi-threading. So basically, with this way, you're manually creating a thread, telling what to do, and then waiting for the result. Here, Openmp will do it for you. So this is what Openmp is based on. So for sure, Openmp is based on the POSIX library for C, but it's not the tool you want to use. So these are the low-level implementation, and you should not think about them. And like I said, yes, I mentioned multi-threading means shared data. Multiprocessing is not multi-threading because data are not shared. Now let's try with some example of multi-threading on, again, on Python Jupyter Notebook. So let's keep going. Okay. So I told you one way to do multi-threading in Python is the low-level way to do multi-threading in Python is with the library threading. If you want some details, you can look for online documentation or just use the help. And with the help, okay, you will get a detail of all the functions that are available, etc. And well, now it opened everything. But in Python, you can always ask for help and reading the documentation the developers providing with the modules. So let's see how this threading use. So when you create a thread, this is an example. So for instance, with threading, you create a thread by saying threading.thread. Okay, this is a thread instance. So Python is a object-oriented language, and this is an instance of a class. You give a target that is a function in this case, and you give a list of arguments that this function should be called. So this is equivalent to the low-level implementation that I was mentioning above of POSIX. So basically, I create this thread. Basically, I'm saying to this thread, at some point when I'm going to tell you, call the print function with argument I. Okay. Then I can simply say, so you see this is a thread that has been initialized. Then I can simply say thread.start, and this is going to start the thread. The thread is running on a separated workflow. Of course, this is a very simple function, already printed Mpi. And if now I inquire what is thread, I see that it's been stopped, it's been completed, and this thread indeed is, if I ask if it's alive, it will tell me, sorry, that's fine. False, because it's already finished. Okay, this is not alive anymore. So now let's change this example with something more, something different. Let's get from, let's import a sleep function. So from time import. So sorry, Panayota, before ask if there is no way to couple Openmp with Python. Okay, that's a good question. As far as I know, there is this, sorry, missed the question. If next time, maybe just unmute yourself, or is it because I will go over. So yeah, that's a good question. There is this PyMP. PyMP is a package that promise to provide in Python something similar to Openmp. So for instance, you can simply say, like here in the example, with PyMP parallel for, so you're saying you want to have 4 threads, do this for loop, and this basically is going to split the sorry, it's going to split the range that you are going to iterate on in 4 pieces and run them in parallel. So you can say somehow it's similar to what Openmp offers, but doing this kind of threading in Python, it's not, that will not work. So we'll show you later, hopefully we have time, while threading by itself does not work well in pure Python. And still, when you want to talking about performance, where you want, I mean, Openmp itself doesn't provide you it is not Openmp provided by Openmp, someone that created a tool similar to Openmp. And it's, yeah, okay, you can try it out, but it's not the same. You want to develop some C code if you want to do some performance optimization of that kind. Because still you're going to accelerate slow code when you accelerate this kind of Python code. So yes, I want to move this away. Okay. Yeah, so in Python though, you can have threading, and let's now do the example with sleep. So what does it mean threading in Python? So it means this, suppose I tell this function to sleep 5 seconds. Okay, so now I'm calling the sleep function for 5 seconds. So now this thread is still in initial state. I start it. You see now my, okay, better, maybe it was better if I was showing you the difference. What happens if I call a sleep function here for 5 seconds? Or in general on another kernel? I mean, let's say a kernel, now it's a sleep because I don't have a kernel to write, but let's say a kernel that takes 5 seconds. If I run this sleep function, basically what you see is that my the interpreter is idle for 5 seconds. It's waiting the result to finish, and nothing else is being processed. If instead I run it as a thread, when this is started, well, this is a started thread and is still alive. And basically, this thread is running, and what I can do other operations. So I'm free to run other things. And what I can do is then to ask to join. And when I ask to join, I'm going to get back I'm going to wait for the thread to finish and get back the result. So suppose I run it again, etc. I ask for join. Now I'm waiting. I'm actually waiting again. But the idea is that in the middle, you could have run other things in parallel, or you can run 10 times the sleep function in parallel. Okay. But this, as you saw, it's not a nice way to, it's again a low-level implementation, not a nice way to deal with the threading in Python. And much nicer way to deal with threading in pure Python is with a thread pool. So a thread pool, it's this way of doing the pool. I will showing you in a second what okay, let's say, okay, this thread pool provided a multi-processing library. So when multi-processing library is a function, a more generic function pool, which is though a multi-processing pool, is not a multi-threading pool. Okay, inside here, instead you find a thread pool that is dedicated for multi-threading. So what if you want to use multi-threading, you want to take this pool. What is a pool basically? Practically, we create a pool of I don't know, 8 threads. Okay, and simply now I can say a function that the pool provides me is a function that does for instance a map. So I can map. Let's take again the sleep function on let's say 5 seconds times 8. So this is a list of value 5. Basically, for each value of these, for each 5, it's running the function sleep. Now, all of these 8 threads are running parallel, sleep for 5 seconds, return the result. Okay. Let's do something more reasonable. Let's define a function that sleep and return. Just I get a value x, I call yeah, anyway, nothing that I write with sleep is reasonable actually. But that's the concept. You get an array. Well, let's do it. Sleep x and then return x. So if now I map a range, okay, let's put also print x. So if now I map a range of 8, okay, now this range is going to give me 8 numbers that are from 0 to 8, so to 7, sorry, that are 0 from 7. So we have a function that sleeps 0 seconds, then sleep 1, another that sleeps 2, etc. All of these start together. So the maximum that this will take is 7 seconds, which is the slowest running. And basically what we get, sorry, I had to call the sleep 2. Yeah, anyway, basically what we get is every second we get a number. We get 0, 1, 2, 3, 4. So each of these functions is finishing, but still this pool is waiting for all of them to finish and returning me the full set of values at the end. So you need to be careful that in this case, when you're using a pool, you are running, you are waiting for the slowest. So while in a multi-threading manner, you can run multiple things. Also with the pool, you can do it. But if you split a task, you may want to split a task in a way that all the threads have a similar workload in order to get at the end a speed up of a factor of 8 in this case. Are there any questions so far about threading? Okay. So let's do some more real example now. So let's take an example of an operation that, let me go back here and take something similar to this. Let's take an example of an operation that in Numpy takes some time. So that is actually slow. And this is, for instance, a sign operation. So let's get one only array of size, and let's apply the assign over all this array. Sorry, X. And this, since it's something that takes time, I will call it only once. Okay. And over 14 should be fine. Well, it is now I'm running. It takes some time, but not too much time, let's say, of course. Just so let's run it over 20. So it's something that it's taking 20 milliseconds to process 500,000 data, to apply a sign on 500,000 data. Okay. So, and let's try to accelerate it with multi-threading. So now I want, for instance, to do a for loop here. Sorry, yes. Yeah, okay, better to copy and paste. So let's try to apply some multi-threading. And so I get an array. And let's take this array and I split it in chunks, like I do here. So I'm splitting this array in a number of thread chunks. And then I use the pool to apply this operation on each chunk. Okay. And I store this as threads time in here. What did I do wrong now? Yes, sorry. The size cannot go from 0 because I need to split it. So let's start from 3 as a power. So what is happening now? So if I put now the time in a logarithmic scale, you can see that we are getting speed up now with by using multiple threads. And let's put here again a log scale. Sorry, now let's extend the range. The log scale is not the best actually, so let's plot it without log scale because you don't appreciate the difference. Though now basically I'm processing, yeah, sorry, I wanted to keep it on X. I'm processing, let's remove it completely, the data on the different threads, and you can see that when I'm using 2 threads, I'm actually significantly faster than 1, and then I'm halving. And then, but in a long range, the 4 threads perform as much as 8, and then 8 performs better. So the multi-threading depends on the region you're looking at. For instance, this logarithmic scale, you can see that with not so many data, it does not provide a big speed up. At the moment, I'm feeding in more data, multi-threading provides a speed up. So here again, yes.
Simone, Panagiotis asks on Slack, what is the difference between threading and multi-processing libraries?
Yeah, sorry, thank you. So yeah, like I said before, main difference between multi-threading and multi-processing is the fact that you have shared data. So let's show you this example. Now I think things will make more clear. There are situations where you want to do multi-processing because you want to distribute your data and not have conflicts between the data. So let's do this example now here. I know I'm sorry, I'm getting also tired, but let's try to, if I'm going too slow, etc., like Ronnie did, please just tell me to go faster, and it's fine. I'm talking about basic things, but it's nice to see them. So what I'm going to show you, it's an issue you might have with multi-threading. So suppose I'm going to have, I have a global variable X, and I just want to increment it. Okay, let's take this example. So I take this variable, I increment it 100 times, and then since it's global, X here changed to 100. Sorry. Okay, thank you. Okay. But also I should accelerate because it's sometimes I get stuck on stupid topics. So yes, very simple topics, let's say. So yes. Let's see what now what happens here. So suppose this is a global variable. We said the data are shared. So I want to increment it, and I increment it 100 times. I get 100. Now let's say I do. I use the pool that I had before, and instead of increment X with one thread, I increment X using two threads. So I map to this function 50 and 50. Okay, so let's reset X equals 0, and let's get X. Okay, map. I use now two threads to increment this function up to 100. Sorry, one thread is incrementing 50 times, another thread is incrementing 50 times, and you get again 100. And you say, okay, what is the issue? Let's now make this 50,000 instead of 50,000. Let's make it much bigger, and so let's make it 500,000. Okay, so I'm going to increment this variable 500,000 times. I increment it twice 500,000. What do you expect? 1 million. I run it, and I get this number. That is not 1 million. What did it happen? It happened an issue that is very common in multi-threading, which is named race condition. So we said that this data is shared between both, and it's living in the memory. And so when one thread is trying to increment it, it takes it from the memory, in this case from the cache. It takes it from the cache, read it in, add one, write it back to the cache. If now I have two threads running in parallel on this data and try to change it, it might happen that both of them at the same time upload it with one value, or both of them at the same time try to write it. So basically one thread is overwriting the value that the other has written. And even if they're proceeding in parallel, this is a problem that you cannot run in parallel with multi-threading and share data. Okay. In this case, you should have each thread incrementing their dependent variable that add them at the end, for instance. So this is something named race condition. All clear so far? So should be fine as an example. So in Python, there is this issue that while as a main pool, they are not offering Python itself. Why as a main pool, they don't offer the thread pool, but they offer the process pool. This is a big complicated issue that is that I'm going to try to explain once. If you don't get it, maybe another time you will get it. It's just a common something that Python has, and it's a critical point that is named GIL. It's the global interpreter and lock. So how does Python work? When I get when I ref a variable, sorry, I kill Skype. If I have a variable A that I say equal, let's give it a value hello, okay? This variable A is initialized here. Then I assign to B the value of A, okay? Now let me import from let me import system, and from sys there is this function get its get reference count, this one. So what happened now? in Python, B did not do a copy of A. B is not a copy of A. Let's do it a better example. Let's take a list. I take a list 1, 2, 3, and then I say B equal A. So you can see that B is 1, 2, 3, and then I do A dot append 4. So everyone that worked with Python until now should know that now A is a number 4 added, but the same as B. Okay, this is because both B and A are pointing in memory to the same object, to the same list object. This is because Python is trying to avoid copying. So if you want to do an actual copy, you need to say, I want to do a copy of A. This is also just a referencing. So this is what is named a reference. So B is referenced to the same object of A. Okay. And this is the way that Python avoids a lot of, improves the performance because avoids a lot of memory copying between big arrays, etc. So it's not copying. Now, though, what happens? Python needs to keep track of how many times the A has been referenced. So how many variables are pointing to this A, because I don't want to delete from memory the content of the array until this is not needed anymore. So Python does not have a garbage collector like Java would have. So this doesn't get removed at some point, but gets removed immediately as immediately as all the variables pointing to this list are deleted. So as soon as I delete A and B, the reference count goes to 0, and then this array from memory will be deleted. So from the system, I can ask what is the reference count of A, and okay, now I have a huge number, 22. Of course, I didn't instantiate 22 times, but this is also due to Jupyter Notebook that is keeping in memory what was this value. So if I delete this cell, for instance, I suppose that now this has decreased to 18 because Jupyter Notebook was keeping track what was the output of a cell. This is what it's doing also for us. So there is this reference count. Now, I just introduced you to the problem of race condition. The issue is that having this is basically in memory. To this array, it's related to a reference count. So every time something is referenced to it is increasing. Every time it's the reference or deleted is decreasing. And so suppose now I assign B equal 1. Now I have the referenced B. And so this got decreased again because this B disappeared. And as soon as this count gets to 0, Python removes from memory this array. If now I use multi-threading, what happens? It happens that if I'm doing the multiple threads are acting on a variable and passing it around, etc., I may run in a race condition for this reference count and lose track of how many times this variable has been referenced. This means that every time a Python instruction is run, this is actually run in single thread. So it's never multi-thread when a Python instruction is run. And this is named global interpreter lock. So the interpreter always blocks and say, okay, now each thread it says, now it's my turn to do something with the interpreter. And one is working per time. All clear? So I hope I explained what is this is a difficult concept, the global interpreter lock, but I hope I explained it. So just to give you an example why they offer now the pool as the multiprocessing pool. So this is another case where you may want to use multiprocessing. I take a function countdown that is counting down a number n from these. Okay, this now took a lot of time. This is 5 millions or more, 50 millions. Let's do it 10 times faster. Well, let's do it. Let's restore the 0 and yeah. This will take now around about one second. So it's counting down a number n that I'm giving. So it's doing a for loop. And if I measure the time of it, takes 0.8 seconds. Okay. Now let's try to do to use again the pool that I had before. So this is the multi-threading pool. If I try to do now this with the multi-threading pool, so instead of counting one down to counting down 1 million, I have two threads counting down 1 million, half of it. If I run it with half, what happened? It's slower. It actually got slower. So Python code, pure Python code, does not get faster with multi-threading because each of these operations gets in the it's due to this single threading. So you cannot accelerate pure Python code with multi-threading. Before we got an acceleration because the sign operation is not done by Python. Like I told you before, it's done by the compiled, by a compiled library. Clear? How do I accelerate now this cooperation? I accelerate it now with a multi-processing pool. So the default tool they provide is this multi-processing pool that it's now if I create this multi-processing pool, so it's creating two different instances of Python. It's like running two Python kernels in parallel. If I run it like this, now it gets faster because actually this operation has been done by two different Python tasks. So this is the difference between multi-processing and multi-threading. This does not share the data. So this is a new Python instance of the interpreter, and the interpreter does not share data with another interpreter. They're running independently one on the other, and they don't see the memory of each other. If they want to talk with each other, they need to talk. And this is what I'm going to focus on the next half an hour. I'm sorry, I think you're getting very tired, but I hope this is useful. And if you have any question, please ask. So this is now a good point to question multi-threading. Okay. So how do we really do things in HPC? In HPC, we do things with Mpi. So we are, like I said before, we distribute data, and we use the tool we use for. I mean, this is one of the tools. It's not the tool, but is on all the systems you have Mpi. It's a standard, let's say. Mpi, it's the standard that is used on any supercomputer facility. Mpi stands for message passing interface. So it is a standard by default. So it defines a set of operations that a library should implement that are required for doing communications between two processes. Okay. So these two processes can live on different nodes, on the same node, doesn't matter. There is an Mpi forum that I think once a year discuss a new version of Mpi. And this is a standard like it's C, C++, whatever. Each programming language is a standard means that you provide just a structure on how your programming language should look like and what it should do, but not how to do it. Then there are various implementations of these standards. And for instance, for the C, you have different compilers. So there is the GCC compilers, that is the GNU is open source compiler. There are private compilers that have different optimizations. So for instance, Intel provides its own C compiler that is optimized for Intel CPUs, etc. But they all implement the same standard that is of C in that case. And this, usually when you talk about C, for instance, you refer to a standard of C or of C++, you say C++ 11, for instance. That means it's the C++ that has been released in 2011. Some years you have different versions of the code. The same for Python. There is Python 3, Python 2, those are standards. Okay. The same way, Mpi is a standard, and you can get, it's supported by, developed by the Mpi forum. And you can get a full documentation on all the Mpi standards. So here it tells you all the list of functions, how they should look like, etc. And if you want to learn Mpi, this is a way to learn it. So, but this is also, it's a huge book. So this is 868 pages, because they also provide hint on how we implement something. So Mpi is based on the MPI is the standard used for communication in HPC, and there are various implementation of it, like Openmp, Mpi, IMPI, that is the Intel one, etc., etc. Like for C, these are different implementation of it. These are libraries that you can load on the system and use them. So like I have here, so you can see tomorrow, there are different libraries available. And well, not here because I'm anyway not there. But if you usually look to the modules available, yes, I know what was the problem. Sorry. If I look to the modules available, you can see that these are all the different software available on this system. And if you look for MPI, you can see that they provide you not here, somewhere in the middle here, you should see that there is OpenMPI, there is Mpi, etc. So you can load them. These are different implementations that you can load them on the need on the system. And so these are implementations. Then in Python, you have the MPI for Pi interface. This is an interface that uses this implementation. It's not an implementation of MPI. It's just calling one of these libraries. Okay. So the main feature of MPI is to define a communication protocol for sending data. Supports parallel I/O, so you have multiple processes accessing or reading or writing the same piece of data on the hard drive. And it allows for non-blocking operation, and it has also dynamic process management. That is what we are going to use also now. So now, since we are short of time, and I expect that I don't want to rewrite all these notebooks, I'm going to show you the Mpi examples that I prepared. So here, how do you use Mpi? Let's start, for instance, with an example. Now I've this is a Jupyter notebook. This is a cell magic for writing the content of this cell to a file. So an Mpi _example.py file will be created. The content of this file is very simple. I say from Mpi for Pi import Mpi, and then this is the communication word. So it's where it's the communicator to use for talking with everybody. And within this communicator, our process will have a rank. Well, the name rank means is a numbering of the process and is an identifier of the process versus all the one available. So it's a unique number of the process that we are using. So I write this one to file, and then I use Mpi run to execute multiple instances of Python in parallel. So in this case, I'm executing 8 of them in parallel. And these all will work with Mpi example.py. Okay. So when I execute this, basically, these Mpi for 8 Python interpreters is run. So this is multiprocessing. 8 Python interpreters run. Each process is part of the same communicator, got a rank, and here you have the ranks of this process that go from 0 to 7. So a rate process, the size is 8, and goes from 0 to 7. The idea is then, based on this number, I use the different process to do different things. And they can communicate with each other. Okay, so this is the standard way of doing, of running MPI in Python and in general on the machines. You have the command Mpi run, and then an executable that has been compiled with Mpi to be executed. What I'm going to do now here, it's a bit on the side. It's not exactly a standard way, but what I want to do here is something you can understand better. So I want to work in parallel here, and I want to basically to have 2 kernels talking to each other. So 2 Jupyter notebooks, two notebooks talking to each other. I want to proceed side by side. Basically, we have 2 of these that we're going to do some operations. And to do so, I need to do some tricky things that are described in these 3 steps. You find it online. Basically, this kernel needs to be initialized with MPI run, so you cannot. These are MPI Python 3 notebooks. It's the same of Python, just they run initialized with MPI. And with this cell, I connect them to each other. Okay, so now I execute a cell on both of them, and I got an output. So now these 2 kernels, these 2 notebooks are talking to each other, are connected in MPI, are part of they have a communicator that is an intercommunicator. Good. So now within our communicator, we have a rank. In this case, both of them have rank 0. This is something specific of what I'm doing. This is, like I told you, it's not the standard way. You're not never going to do this on our systems. It's just a way to show you in parallel. So both of them got rank 0 just because it's an intercommunicator. And so basically, we're just talking between 2 ends of different MPI execution. And so both of them have a rank 0 within each size, but just because I didn't run other kernels. So if I would have run other kernels, this one may have rank something. If I had 8, may have made rank another different rank, but both of them now are rank 0. So now I want to send a message. So I want to send a message between the 2. I say the destination, and I say, this is what I want to send. Okay. I send something, the receiver, okay, at the moment, let me split it here. I send something from the server. Now you see there is an asterisk because I'm waiting for the other one to receive it. So if I split this one, I run here receive, I got this message, hello from server. So this is sending and the other is receiving. So we have in parallel 2 calls, one is sending, the other is receiving something, and I can do the opposite here, send and receive. So basically this message is sent. Questions? Okay. Another way to do, another thing you could provide here instead of only the destination is to a tag number. So you can tag your message with a number. This must be an integer. And so now I'm sending 3 messages with the different tags, because if you are sending a lot of stuff, you want to be sure that you are getting the correct message from the correct sender. And so the tag helps you to do that. So now I'm sending 3 messages. And here I'm getting first the tag 3, then I take the tag 1, and then I'm taking what is left, that is this one with tag 2. So if I don't provide a tag, means that I take any tag. If I provide a tag number, I take a message, I look for a message that has that tag. Okay. So this is what MPI provides, some sending function, receive functions. This looks pretty basic so far, I suppose. Now, is there a timeout threshold? There are sometimes it may happen that there is a deadlock, so it's always useful to have a timeout threshold, because suppose here I say receive, I'm waiting, but nothing is sent. So if I did something wrong, this should stop at some point. There is, but usually it's of the order of minutes, because but it depends on the implementation, but it has a very big value. Usually it's just don't run for days, but if after 1 hour you stop, because they cannot force you to be within 1 second. So they put a number that is huge, like 1 hour. So now in order to release it, I need to send a message. So let's now send a message from the client. So now I'm sending this another message. A last parameter you can give to a receive function is a status. So the status provides you some information about the message you received. Suppose you don't want to give a tag, etc. You want just to receive a message. The information about this message will be stored in the status. And then you can look at which one was the source, what was the tag of the message, and what was, for instance, the size of the message. I run it, and I got this another message, and this has been received from 0. The source is 0. The tag was 57, is the one I gave here, and the size of it was 25 bytes. Okay. So the Python implementation of it offers you two very high-level functions that are com receive and com send. Okay. There is another one that I'm going to explain now that is receive with the R capital. So when I do this now with arrays, suppose, let me say, started from here. So I send a random array, and from the other side I receive it. So far worked fine. I just had to say send the array, and this is got I received it and it's been stored in array. No problem so far. Okay. And now if I do the same, suppose with something that is size 1, I send it on the other side, and I get it, and basically I got one number with a message that had size 163 byte. For someone that has an idea, this is a huge size of it for the message for one number, because one number should have a size of 8 bytes. Why is this? The reason is that these very high-level function that are provided by Mpi for Pi receive and send, they don't actually send only the data, but they use the Pico protocol. So your array, exactly, what they send is not only the array, but they send all the information about what the array is. So they say that is a Numpy array, etc., etc., etc. Because on the other side, I want to be able to reconstruct the full object. So this is the Pico protocol, and if I say here import Pico, and I say pico.dumps R, basically what is sent to the message is this string here. That is this fully describing the object. So if I get this string now, and I provide it to Pico loads on the other side, here, it's able from this string, sorry, not dumps, loads. It's able from this string to reconstruct the object as an array. It's a serialization of the object. But a lot of data is being sent for nothing, for one number, okay? What is the best way to do communication in case of Python, in case of array of data, is to use the capital send and capital receive. Now, when you use capital send and capital receive, only the data is sent as far as you provide NumPy arrays. So these are specific functions for NumPy, and only the data, only the number, these 8 bytes are sent around. The important though is that on the other side, you have an array that is defined with the correct size and the correct data type, okay? Because if now I send this message here, I get it and I got it, and only 8 bytes has been sent. Suppose now I locate 2, an array that has data size 2, so an array that has a shape 2, so it's made of 2 numbers. I send it, I try to receive it. Okay, only the first one has changed. So this wasn't a big problem because I sent less than what I got, than what I actually located. So only the first one changed. If now I send on the other way, I send 2, and here I locate only 1, then in this case we run in an error because we tell us I received 16 bytes, but you had only 8. At the same way, you run in an error if you have a different data type. So suppose these are 8 bytes. A size of 8 bytes is also a D type integer 64. So this is something that also size 8 bytes. But if I send around this data on the other side, and I store it in a D type integer 64, no error got in because the only information I sent around are the 8 bytes. So I cannot say know from this side what these 8 bytes represent. But if these 8 bytes are interpreted as an integer, well, you get this garbage number and you don't get 0.9. Clear? Questions? Okay, 10 minutes more. Let's go to the end. There was a question. Yes, of course. I'm saying this because this is the correct way to send data around performance-wise, because you don't want to send around all this data for 8 bytes. Okay, so this is the correct way to send around the data, but requires a bit more of attention. Okay, yeah, I ran the wrong side, doesn't matter. It requires a bit more of attention. Okay. Now, another kind of operations you have, and this is the last feature we see for MPI today, because we've left of time, we ran out of time. So just to give you an introduction, what you do with these kind of tools. Another feature they provide you is non-blocking operation. So together with the send and receive, you have an I send and I receive. So I can put an I in front of it. I means it's not blocking. So it means that this is going to be given to a thread, and a thread will be responsible of the sending and the receive, but my main thread is not going to be blocked for it. Okay, so when I run I send, this is I sent, has been I sent, and it's been sent in a non-blocking way. When I run I receive, also here, this is what I get out is an MPI request. So here, this is just something that in the background is waiting for a message, but we don't worry yet about what. And we get the message with the wait. So when we say wait for the request, we say wait, we get the message. So doing the opposite way, I say I receive, I got already a response. So this cell is already active. I can do other things. And then when it's needed, I say wait. And now, for instance, we are waiting because there is no message sent yet. And I will run out as soon as the message is completed. So it's the same thing we saw before with multi-threading. So we are waiting for the message to be completed. Okay, let's do a practical example and we are finished. I hope you could follow and you're not too tired. So this is the last example. How would I implement a matrix vector product in a parallel manner? So let's consider the operation ix plus y. If I split the matrix in domains, so I consider a domain A1, A2, A3, A4, and I split also the X into domain X1, X2, doing the operation AX plus Y means doing A1 times X1, A2 times X2, sum together, these give me the Y1, and then I do A3 times X1, A4 times X2, and I get the Y2 component. I hope this is clear for whoever knows matrix multiplication, this will be clear. So this is how you do the matrix. How would I implement it in parallel now? I would assign to a process the top part of it. So I assign to a process the top part of this matrix and array, and to another process I assign the lower part of it. Okay. So how do I do that? Suppose the matrix size is 20. I split the number in two. I get 10 in this case. And then, okay, here as well, I split the number in two, but I do n minus half just to be sure that if this is an odd number, I get the full remaining of the matrix. So if this was an odd number, this was the even part, this is the odd part. Okay. Then my top part of the matrix looks like this. It's a matrix that has size m1 n. So n is the its size on the longs, its number of columns, while m1 is the size of x1, so it's the number of rows. x1 has size m1 only, and x2 has size m2 only. Okay. If now I want to do the operation, basically what I want to send around is the vector. So on the other side, on the client, I do the same operation. I just allocate the matrix for the lower size. This is the lower size of the matrix. And And then I allocate the x2 component. The x1 component, I have it here, but as zeros, because I suppose that this component is the one of the process one, the opposite here for x2. So if you think about the size of it, what is convenient to send around is the half part of the vector, and not the matrix, of course. So we have the two matrices on the two sides, and we send around the half part of the vector. We want to send it around because we don't know what is the half part of the vector. If suppose we do multiple operations, this half vector is known only on one process, and this other half of the vector is known only on the other process. Unless we ask for it, we cannot do the, sorry, unless, what I was saying, unless we don't ask for it, we cannot know what is its value. So basically what we do here, it's we want to send to the other one, the x1, receive from the second process, x2, the opposite for this client. So we are sending x2 and we want to receive x1. And then we get y that it's for each one of them, one in one case the upper part, in the other case the lower part. Okay, so here I'm doing basically this operation. This line, the upper line here, the lower line there. Okay, so I run it, both of them, and I get this result. So they've run in parallel. I got the upper part on this side, the lower part on this side after applying the multiplication. This is, for instance, case where you want to optimize this code with non-blocking operation, and you want to do so because this task, since I already know x1, this task I can perform it in advance, and then do the communication in the meanwhile on the background, and then perform the second task after I get the result. So this is an example where you may use the non-blocking. And so at the beginning, I start to send with I send and I receive the data. I do the operation I can do because these are all local data. I wait for the result, and then I do the second part of the operation. So this is the optimal way for doing matrix vector multiplication in parallel. I would like here to do some timing and scaling, but we are really out of time. So first of all, 2 points. If I'm open to take any question, but before taking question, maybe it would be good to send around a questionnaire link that we prepared. So if Christos can send around the questionnaire, we prepared a questionnaire for this first day to get a feedback, and will be very helpful for us if all of you can fill it up. So Christos, do you want to say something or just send it to the chat?
Yes, thank you, Simone. Just very quickly, I will share it now in the Zoom chat and also in the Slack channel. Really helpful for us, and we really appreciate getting this so that